Let's find the solution now for problem 30 in page 92. What are the final hydrogen ion concentration and the pH of a solution obtained by mixing 250 milliliters of 0.1 molar citric acid, polyprotic acid, okay? 250 milliliters of 0.1 molar citric acid Again, this is a polyprotic acid. You have to be careful how to deal with this problem. And mix with 300 milliliters of 0.1 molar solution of potassium hydroxide, KOH. 0.1 molar KOH. Also give us the pKa. pKa is for citric acid. 3.06, 5.74, and 5.40. So right there we know that they have 3 protons, right? 1, 2, 3 protons. Let's forget about these and start with the dilution. That's the way that we approach this kind of problem when you have mixtures. Let's start with look at the dilution for citric acid. Again, when you do that, you forget about the reaction. You think about only by the increase in volume what's happened with the concentration. We talk about the reactions later. So M1V1, M2V2, the form that we have been used for this kind of problem. We have 250 milliliters, 0.1 molar of citric acid, and the final volume now is 250 plus 300, 550 milliliters, okay? And then we calculate the final molarity for citric acid. If this were just a dilution, this would be, the molarity would be 0.045 molar for citric acid. Let's do the same for potassium hydroxide, 0.045 molar. The same for potassium hydroxide, 0.1 times 300, 0.1 times 300 equals the molarity final versus the final volume against 550 milliliters, and the molarity for potassium hydroxide is going to be 0.054. It looks a priori as potassium hydroxide was in excess, but it's not the case, because it's in excess if it were only 1 proton. But this species, citric acid, has 3 protons, so don't get it wrong in here, right? So remember, citric acid, we just write generically H3CA, dissociate first in H plus and H2CA minus. That will be the first Ka. Then H2CA minus dissociates to give off the next proton, and it becomes the species HCA2 minus. That will be Ka2 for this equilibrium. And finally, HCA minus give up the last proton and generate an equilibrium of H plus and Ca2 minus. That will be the Ka3. Look, potassium hydroxide has enough to kill the first proton, the 0054, and there's only 0045 of citric acid, right? So the concentration of hydroxide is larger than the concentration of the first proton for citric acid, right? 0054. So it kills off the first proton, consumes entirely the first proton from this. Therefore, the first step is going to be gone, no equilibrium anymore, because you suck up all these protons from the first step. Okay, 1, 0.045 would remove entirely 0.045 of KOH would remove entirely the first proton, right? So if you remove the first proton, there will be no equilibrium. So the first thing we know here is this does not involve the first step. First step is gone. So we had 0.054 of potassium hydroxide, and you use 0.045 of that to neutralize the first proton from citric acid, 0.045, to neutralize the first proton of citric acid. What's left over then is that we have 0.009 of sodium hydroxide. This was for the KOH concentration. And this, the OH 0045 is the OH used for the first proton. And now what left is 0.009. So what's this 0.009 is going to do? It's going to neutralize 0.09 of hydroxide. So what did we have in terms of a species H2Ca? That we have that species the same concentration of citric acid, 0045. So what's going to happen is that H2Ca now is going to be equilibrium with H plus and HCa2 minus. We're going to use 0.009 hydroxide equivalents to neutralize this and push this reaction to the right. So initially you would have 0.045 H2Ca, but the 0.009 is going to be used, and H2Ca minus is going to remain at 0.036 in this equilibrium. Okay? Where the rest go? The rest goes and became HCa2 minus. Okay? Let's go to the next page and rewrite this thing and make sure that you understand that very well. Okay, that's important because this was H2Ca that was initially generated and is going to be now in equilibrium with this as an acid and a conjugate base. So this is a buffer solution that we have right there. Okay, let's rewrite this thing here. H2Ca minus come on, the pen is come out now. Okay, H2Ca minus in equilibrium with H plus and the HCa2 minus. Okay, so we had 0.036 from this species and the 0.009 from the other species here. The acid is 0.036 and the conjugate base is 0.009. 4.74. Oh, that's already given. Again, this is a buffer solution. So if it's a buffer, how do you calculate the pH of a buffer? We use the Henderson-Hausenberg equation. Again, this is a buffer because we have an acid in here in equilibrium with a conjugate base. Now is the easiest part of everything. We have pH equals pKa, but in this case it's going to be pKa2 because we're talking about the second step, plus log of the concentration of the conjugate base. In this case here is going to be HCa2 minus, divided by the concentration of H2Ca, the acid. Then pH is going to be equal, for space here, pH is going to be equal 4.74 plus logarithm of 0.09, right, HCa minus, just look at there, 0.009, divided by the concentration of H2Ca, that's going to be 0.036. We plug in all these numbers, we calculate, it gives the pH of 4.14. Now, if you have the pH 4.14, we know the concentration of protons. That's going to be concentration of protons 10 to the power of negative pH, right? The inverse relationship of pH. Concentration of protons equals 0.000072 molar. Let's put that in scientific notation. 7.2, 10 to the power of negative 5 molar. That's the concentration of protons.